reputed journal, having very rich experience of project and different funding agencies. So without taking much time, I invite Professor Kaushik for presentation. So, thank you very much, sir. Thank you for this beautiful introduction. Actually, I'm going to start with dynamics of the geophysical plasma events. And the main part is the quest for the materials suitable for the deep space. In fact, let me clarify in the first slide. Uh, the topic is related to the space physics. But because we need the materials, we need the sensors, and they should be capable for bearing the temperature and the uh, deep space conditions. So we'll discuss that. Few slides in the beginning, although the students are not much here, but this is for them. In case they are pursuing the research, they can go for the science, astrophysics, condensed matter physics, nuclear physics, electromagnetism, etc. And then introduction to the common physical processes, the basic areas of research, introduction to the institutes offering uh, facilities for the research. Then they have the common physical processes. They can be well understood by fundamentals acting behind them, mechanical. Then we have the thermal processes, Planck's law, electrodynamical processes. You are well familiar with the Maxwell equations. And we have heard the first lecture by Professor Harboleser that was on quantum mechanics. So all these phenomena are intercorrelated and open for the research. Again, coming back to the astrophysics, there are two things there. One is the theoretical, another one is the experimental. Because yesterday's sir has said science has to prove itself. So once the theory comes, that should be verified by the experiments. So theoretical astrophysics, they can go for the fundamental forces which are existing in nature, electromagnetic, weak, then strong nuclear forces, gravitational forces, etc. They have particle physics, open space. CERN is providing very good facilities there. Then we have experimental astrophysics. What they can do there? They can have the observations for the solar system from the galaxies, GMRT facility in Pune for that, and then we have the observations regarding the composition of sun. Basic areas, fundamental research, applied research, then fundamental research includes the basic sciences, physics, chemistry, mathematics, bio, etc., etc. N number of fields are there. Then we have the areas in human performance, so control, population science, etc. Then biophysics, plasma physics, computational physics, and these are for the many for the students institutes which are providing these facilities at advanced levels. Some more institutes where they can apply for this research. Uh, Apart from this facility, they provide the fellowships also in terms of summer fellowships, winter fellowships, then proper research options by screening test. They take their own text exams there. Then after 12th standard, they provide the fellowships also. So now coming back to the main topic. So what we have here, we have a beautiful start. And this is what giving the continuous particles energy, which we are receiving. And this is what we are having 24 into 7 into 365 days. So this plasma when comes very close to the Earth in our magnetosphere. You know that at polar regions, the thickness is 30 to 60 kilometers. But if you go for the equatorial regions, the thickness becomes very high. It is almost 350, 350 like this, 400 kilometers like this. So what happens? This is the side from where the plasma is coming. This is sun here on this side. This is our Earth, the polar regions. And I think it will play here. Anyway, um, actually, what I wanted to tell you here is that plasma is coming from this side and it interacts with the magnetic field of the earth and causes. Yes, sir. Uh, that we see in the polar regions and the plasma is interacting. And it comes to the reconnection. The reconnection that takes place here what is Earth area. And when it comes back to the polar regions, it gets the favorable conditions, it enters to the magnetosphere and creates the lots of activities. So all these is the satellite regions. We are working on that. Now, what is the main quest here is the materials uh, which can provide us the data at lower cost. And secondly, because the situation at the upper environment is not favorable, temperature variation is very high. Sometimes goes minus 150 degree, and on other side it goes up to 120 degree. What we need here is the materials which are suitable for the space missions. They must have the strength to weight ratio, thermal stability, radiation resistance, and long-term durability. So the space radiation detection is fundamental. Uh, that covers the bit of astrophysics. We have the planetary explorations for that. Then heliophysics. Heliophysics is the region where the sun's influence is taking place. Uh, then we have the astronaut safety, gamma ray burst, another phenomena of the flares that continuously coming from the surface of the sun, the cosmic ray detections, and high resolution spectroscopic detectors that we need here observe such kind of activities, such kind of events. So the one component or the sensor that we use here is the cadmium zinc telluride. I will see its applications also. So it has the devices we are in mission applications successfully at lower energy terms also. So other alternatives of that CZT uh, sensors we have the high purity germanium detectors. They are provided superior energy resolution, but the drawback is that they need a higher temperature, and that's we need the cooling for that. And cooling itself is very costly. So the cooling system must be there, and it enhances the cost as compliance of the satellite missions and power consumption, mechanical complexity, and finally, we can see that this is undesirable for long duration space missions. We cannot afford such kind of the luxury in the space. So CGIT, why we prefer that? Because high effective atomic number, wide bandgap, high density, and direct convergent detection mechanism. It enables compact solid state and operating at the ambient spacecraft temperatures. Whenever we need to detect some event, we can open the door of the sensor and it provides us accurate data. And that too at the spacecraft temperatures or the normal temperatures. The structure and material composition. Then we have zinc plate cubic structure that is constant decreases with increasing zinc concentration, direct band gap semiconductor, and in addition to that, increases band gap, it improvises the resistivity, enhances the mechanical hardness, and reduces the defect density in optimized growth processes. It has the wide application in field of space physics, structural frames for launch vehicles components, engine parts due to oxidation resistance at elevated temperatures, and on other side of the space, when we go to the deep space, uh, you can say up to Moon, Mars, and Jupiter, etc. High strength and aluminium while remaining lighter than steel. Excellent fracture toughness, fatigue life, and relatively low thermal expansion. That is the benefit of using such kind of the sensors. Then we have the other alternatives also, like temperature alloys. You can use the nickel based super alloys there. Uh, the properties. They retain strength above than 700 degrees centigrade, resistant to creep and oxidation, But apart from that, there are the challenges also. The higher density than aluminium or titanium. So uh, we can summarize that the difficult machine and processes. The other alternative is polymer and fiber reinforced composite materials. So what we have here, the composites have revolutionized spacecraft design due to low weight and customizable properties. And what we use there, we use the carbon fiber reinforced polymers for that purpose. The other alternative, other than this, is the composition, the fibers embedded in epoxy or polyimide matrices, and they have the advantages. The tensile strength is very high. The density going to be quite low and tolerable stiffness by fiber orientation. And their applications, satellite structures, payload fairings, deployable booms and antenna supports. And if we talk about the performance, sensitive to environment degradation unless properly encapsulated. The second one, matrix selection crucial for thermal stability. So these are the plus minuses using these carbon fiber reinforced polymers. Then the part comes with the testing and qualification of space materials because we need to consider several things together. We need to see the cost of the mission also. We have to see the life of the mission. So, but before the flight, materials undergo rigorous testing, thermal vacuum testing, vibration and shock analysis. They are exposed to the radiation also. Atomic oxygen erosion, micrometeorite impact experiments, and qualifications ensures mission success and crew safety. If all these are okay, they're found quite satisfactory. Only then the specimen is approved for the space mission because it's a costly affair. You cannot afford it by very small mistakes. So now coming to the second part here. So uh, mainly I will discuss here the source. That is the solar X-ray spectrum that was launched by the PRL scientist Professor Atmanjev. I have honored to work with him. And then recent developments, apart from these Aditya or AstroSat, we are going to talk about Gaganyaan also and several others, the future missions. So this is what I wanted to talk here in the source. That is the east position in the upper one, that is 12 of 12 o'clock. So this is and continuous tracking. The schematic diagram of SLD payload, the prototype, and this is what we have to cover. That summarize here. The sun is continuously giving its plasma coming to the earth. And interestingly, we have the Voyager 1 and Voyager 2. Hope you have heard. Voyager 1 has gone beyond the atmospheric limits. I mean, the range up to where the sun has its influences, it has crossed that limit. And that's only one light day. Ah, this is the where we are interested to do the research because data is coming at this level. This is the L1. And why this study is important? Because all these things are intercorrelated. Sun Earth has produced the varying radiation continuously coming in terms of solar wind, high speed winds, slow speed winds, and then we have the energetic particles, solar energetic particles, SEPs. They have the various winds. And having these three varying things, the radiation, the solar wind, the energetic particles, we have the interacting solar wind, energetic particles, and after having the variation and interaction, we have how and why the sun vary. Because apart from its size, apart from its activities that we have seen in the movies, the magnetic field is changing its direction continuously. In 11-year cycle, the polarity of the sun change from north to south and south to north. Then how do Earth and planets respond to that change? What are the impacts on the human? This is what you see here is the 11-year cycle from maxima to minima, and this is up to 2017 that we have here. Interestingly, we are having the cycle 25 nowadays. So maxima, what we have at that moment, the increased flares, solar mass ejections, and radiation belt enhancements. 100 times brighter X-ray emissions during the maxima times. Increased heating of Earth because the plasma is coming large number. So heating also increases during these times. And on the reverse, at the declining phase, high-speed solar wind streams, solar mass ejections causes the geomagnetic storms. The variables are, I think it will play, unfortunately not. So I will skip the slide. Coming to the results, that is what we have the solar X-ray spectrometer by Dr. RJIT, designed by PRL, fabricated by Space Application Center, Ahmedabad, and it was launched on onboard GSAT 2 missions. The mission life was 5 years, but interestingly, it worked for 8 years. The science from this mission contributes to microflares in heating the solar corona because we have used the CJT sensors there, and they have provided the energy in very low energy range. Short and long-term variations of the solar corona, coronal seismology, and they have solved the problems how and when the solar flares affect the terrestrial environment, sun earth connection, and space weather. This is our results, the simulation results we have. The if you want to summarize, we have fast solar wind velocity, high solar wind density, and strong IMF. And as a result of these three, we have the very strong solar wind dynamic pressure. Our results this is the plasma entering to the Earth the simulation. Coming for some more results, I'm just skipping these slides. This is when the magnetic field turning is towards the northward IMF. This is what you have the northward IMF. Our results, some more results, the ions concentration that we have plotted, published results, and we care about the hydrosphere. Why is it important? Because it provides us the light. Suppose magnetosphere is not there or the Earth's magnetic field is not there, can we survive? The answer is no. The future trends, the development of materials for space driven by need of lightweight, high performance materials they can enhance the mission life, demand of multifunctionality by the small payload. We need to have some more science. In some uh, then extended mission durations, cost reduction through additive manufacturing. This is the most important part because cost is going to be very important. And the last one is the sustainability via in situ resource utilization. And the science is changing because we are using the nanotechnology with smart materials and composites.